So we're going to start today by talking about the parent functions of different what we call function families. And you have or should have a worksheet in front of you that has 8 problems. And this little tiny video here is going to walk through those. And I'm sort of thinking that pretty much the first 6 will be good, at least maybe 5 out of the 6. And then when we get to the back, that's where I'll slow down and make sure that we're good, okay? So make sure that your worksheet becomes a reference document. Make sure it's 100% correct as we go through this. So the first one that you were supposed to graph was f of x equals x. You're, again, making a table, the fav5, and we're going to give domain and range, y-intercept, and the x-intercept. So I'm going to just show you the answer because you should have already graphed this. And so you should have had -2, your fav5, they're all equal. When you plotted it, you would get a line. Please make sure you do have a line and make sure there's an arrow on both ends. This is called the linear family, so you're going to want to write that on the line on the worksheet. Your domain and range are both everybody, and it crosses the x-axis at 0, and it crosses the y-axis at 0, and that is a linear function. I'm expecting that one would be 100%. If for some reason you need to, just pause the video if you need to fix anything. Otherwise, I'm moving on. The second one was f of x equals the absolute value of x. So this time, anything that comes out of the absolute value would be positive, which means it's going to change the look of the graph. And as we've had some experience with already, it makes a V. So over here, we see some symmetry happening, and we also notice a bend up. This is called the absolute value family of functions. This is the domain of everybody, and the range is 0 and greater, 0 to positive infinity with the 0 included. And again, it is crossing at x-intercept and y-intercept. And I should be mentioning as I go through these that these are the most basic function of each family. So they're called the parent function. And everybody else, once you know what the parent looks like, you can tweak that and change that. And that's where we're going to go in a couple of minutes. Oh, I should also mention before we go, sometimes like when you see an absolute value function, your fav5 might fail in finding the bend up, and you need to be smarter than that. And sometimes you have to use more inputs to find where it bends up. This should not be a line. You know it's a V. So if your inputs are not showing you where it bends up, you've got to use more inputs. Okay, so the next one is taking your input and squaring it. So again, the fav5 would be good choices. And I would again think this one would be pretty solid. Just be careful to make sure that these are both positive, because no matter what number you raise to the second power, oh, by the way, to any even power, it should be positive. So again, we have a bend up here, but this time it is a U, and these are called quadratic functions. So that's what you want to write on your line. That's the name of the family, and this is the basic quadratic known as the parent function. Everybody can go in as an x, but again, 0 inclusively and up and greater to positive infinity is your range. And again, we're meeting at that 0, 0 for the x-intercept and the y-intercept. So the fourth one is something new. We're raising it to the third power. Now, again, our fav5 are going to be okay as inputs. But this time, because we're not raising it to an even power, we are going to see negative outputs. So your table, if you use the fav5, you should have a -8 here, because -2 to the third power does give you a negative, and the same for the -1. And so instead of getting the U, it's like you've got a half a U here and then a half of U opening up, down, if you notice that. Once again, though, your inputs can be everybody. And as you look at the graph, your output, your range can be everybody. But again, because we're crossing through the origin, our x-intercept is 0 and our y-intercept is 0. And the family name is the cubic functions. Cubic, cube being that 3. And I call this symbol, like this graph, I say it kind of looks like what I call the hurricane symbol. If you've ever seen on the Weather Channel, or they kind of have this symbol that kind of resembles this. So a cubic gives you that kind of a look. Okay, the next one is f of x equals the square root of x. And here's the first one where our fave 5 are going to fail. So we're not going to use our fave 5 because on the real number system, putting a negative under the square root is not going to work. So our minimum input in this case would be 0. Now wait a minute, Mrs. Woodruff. Why these inputs? Just because I'm trying to make the outputs also be, in this case, whole numbers. So I am picking perfect squares. So the square root of 0, the square root of 1, and so forth. So if you didn't do that, you might want to change your chart to see that. Okay, let's take a look. Sorry about that. The dog just tried to come in. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. And remember that a square root is asking you what number times itself. It's not a division. So 3 squared is 9, 2 squared is 4. A square root is the opposite of squaring. This is the square root function. This is the most basic of the square root function. And you're going to notice it actually looks like half of a U laying on its side, if you notice that. And to be perfectly honest, the square root of 9 actually can have two roots, a positive and a negative. So we could have put a point down here at 9, negative 3, and we could have put a point at 4, negative 2, but that would not be a function. It would fail the vertical line test. So we're only going to look at the positive roots, which are called the principal roots here. Otherwise, we wouldn't get a function. But it is a parabola laying on its side, which shouldn't surprise us because remembering that square root is the opposite of squaring. So it's just oriented a different way. Now, this time we're finally seeing a domain here that is not everybody because we're not going to put a negative as an input. So it starts at 0 inclusively and goes up to positive infinity. And the range is doing the same thing. And again, we're kind of right at that origin for crossing the x and y axis. So the x and y intercepts are both 0. And that's the most basic square root function. All right, now this is 2 to the x, where you're now going to make the exponent change and vary. And it is okay to put your fave 5 in there. And you are going to have to use the exponent button on the calculator, which in the calculators in the classroom look like a little teepee. It's like the little insert caret. Some calculators, the button might be y to the x. Some might be x to the y. And of course, some calculators, if you're really looking at kind of an older one, I believe, has an EXP exponent button. So I am going to use my fave 5. And if I take 2 to the negative 2, and you might not remember this from Accelerated, but I promise you will by the end of the year, but a negative exponent basically reciprocates this. So instead of being 2 to the second, which would be 4, it would actually be 1/4, which is 0.25. Same thing, if we have 2 to the first, it would be 2, but 2 to the negative first would be 1/2, which is 0.5. You might not remember that anything to the 0 is 1, not 0. And of course, I would imagine these were pretty easy. 2 to the first is second, and 2 to the second. 2 times 2 is 4. I plot these points, and we're getting, we talked a little bit about this with our geometric sequences in the first unit, but we're getting an exponential growth curve, basically. Everybody can go in, but not everybody can come out. And if you were to pick -3 and -4 and -10 and -100, this would get closer and closer to 0, but it will never reach 0. It's called, this is approaching 0. So the range would not include 0. It would be a parenthesis, but it would keep going up. And this, again, is what we talk about with exponential growth. So if you're talking about, like a virus, this is what they talk about with the curve and wanting to flatten this, wanting it not to shoot up so rapidly. More on that to come in Unit 7. The x-intercept, there will never be one. and the y-intercept is 1. And I had to do this by hand, and some of these graphs look really lousy because I'm doing them with a mouse, but I kind of missed that point in trying to do that. Sorry. So now when you flip over to the back of the worksheet, we are going to hit two that you've seen this one, believe it or not. We did talk about the greatest integer function, or rather it's also called the step function. And we did that back on a homework assignment that had a problem about the parking garage and the cost of the parking garage. But basically the greatest integer function, the output is the greatest integer that is less than or equal to be honest, the input. So if you look at, for instance, and I'm going to start with the positives because it makes more sense here, but when you get to the negatives, people kind of get twisted around. So 2.1, the integer that is just less than that would be 2. For 1.9, it would be 1. For 1.2, it would be 1. And for 1, it would be 1. For 0.5, it would be 0. And for 0, it would be 0. And negative 0.5, now this is where it gets tricky. Actually, the smaller integer, because the negatives go in the opposite direction, would be negative 1. Negative 1 would be itself, negative 1. Negative 1.5 is going to go down to negative 2. And now we're going to jump negative 2.3 would go down to negative 3. So you might want to pause the video and see if you can just do what I just said and fill it in. And then I'll flip over and show you the answer to this one. But what it's going to end up looking like is a series of steps. It's going to jump from one integer to the next. So to show you what that looks like, now here is the table I just mentioned. So now if you come to 2.1, it's going to be on the step here, anything greater than or equal to 2 up to 3, not including 3. So 2.9, 2.997, 2.9999998, they're all going to be an output of 2. So it creates a step. And the inclusive piece is the actual integer, the 2. But then when you get to 3, it's going to jump up to the next step. So that's kind of what we see here. If you look at the 1, 1.9 is on the 1 step, 1.2 is on the 1 step, and the number 1 is on the 1 step. And it's sort of like once you get the first couple of stairs, you get sort of how to fill the whole rest of the thing in. The domain of this, everybody does go in. So, and it is a function because notice if we were to draw a vertical line on negative 2, we have an output of negative 2, but this is not inclusive. So there's not 2 here. So it is a function. But the domain, can I put in negative 10? Sure, it's down here. Can I put negative 7.5? Sure, it's on this step. Every possible input can go in. Now the output, when you turn your head, is only integers. So you're never going to get an output of like 1.5. You're never going to get an output of negative 5.3. So the range would just be integers, and that's the jump. The x-intercept, there's many. There's an infinite number from 0 inclusively up to 1. So all the numbers in between, 0.9, 0.8762, 0.3, right? They're all part of the x-intercepts where it's lying on the line. The y-intercept, though, there is only 1. So this step is the only one that hits there at 0. So again, I would pause this and sort of fix my graphs so that you have the parent function of the greatest integer function. Now, as we move forward, the next one is not a parent function. It's just showing you a new kind of function that we need to introduce you to. And again, this is just, getting comfortable with kind of different kinds of functions. So this is called a piecewise function, and that word will show up on the next slide. And basically what this is you're going to use 3 different functions. So f of x equals 2x plus 6 is going to be used for part of the domain. F of x equals 2 is going to be used for part of the domain. And f of x equals 11 minus x squared is going to be used for part of the domain as well. So basically, if you look here, for all the numbers up to and including an input of 2, So for all of these numbers up including to 2, you would input into the top function. For all numbers, actually that's supposed to be -2. I had fixed it and I just realized that that didn't happen on this slide. So all the numbers up, excuse me, to -2, we're going to use the top function. Between -2 and 3 inputs, we use the middle function. And for 3, inclusively and greater, we use the bottom function. And why it's called piece, and I do not mean like the sign of peace. I mean PIECE, like a piece of something, a piece of candy or something, is you're going to have 3 different pieces. And sometimes they'll come together and sometimes they won't. So basically, I'm going to go on to the next slide to talk about how to do the inputs for this one. So you see, I did fix it up there. I just didn't fix it on the other slide. Okay, so you're going to notice I'm color coding this. So for all of these inputs, notice that they fall in to this piece of the domain. So -4, -3, -2, I'm going to use the 2x plus 6. So when I put -4 in, 2 times -4 is -8 plus 6. So the output would be -2. When I put the 2 times -3, I'm going to get -6 plus 6, which is 0. And 2 times -2 is -4 plus 6, which is 2. Did you just hear Mr. Woodruff really sneeze in the background? I wonder if that came through. Anyway, now when I get to this next one, I really shouldn't be using -2. It's not part of the domain. However, I kind of want to see where this guy is going to start. I'm going to put an open circle. So I'm actually going to put that -2 into this function. And basically, this function, everything you put in, you get 2 out. So for this piece, it's just if you put in if you put in 0, you're going to get a 2. If you put in 1, you're going to get 2. The output is always 2. But I'm going to put the -2, even though it's not legal. And I'm going to put the 3, even though it's not legal. And I'll show you why in a second. Well, that was easy. So now this one, -2, 2, for this, we'll have an open circle. And the 3, 2 is going to have an open circle. And it's just going to let me know where the sort of the next piece starts. So finally, when I go to 3 and 4 and 5 and 6, if I wanted to keep going, they have to go into this one. So take 11 minus 3 squared. 3 squared is 9, and 11 minus 9 is 2. And if I put the 4 in, it would be 16, and 11 minus 16 is -5. And basically, I start coming over and I start plotting my points. But remember, that we're going to kind of have an open circle. But notice they join up. Okay, so let me show you the graph. And oh, by the way, piecewise, that's the name of this type of function. Okay, so here are the 3 green points. There's the -4, -2, the -3, 0, and the -2, 2. Now, when I go to do the -2, 2 for the blue guys, see the open circle? But the green one nicely filled it. These are going to connect. They don't always connect, but the next piece does connect. And then here are the -1, 2, 0, 2, 1, 2, 2, 2. And then remember that the 3, 2, 3 really isn't supposed to go in. That would be an open circle, but really cool. The next piece plugs the hole. And there's those 2. And notice this is going to be part of a curve because this is a quadratic. Notice that this is part of a line because that's a linear. And the other guy is also a line. It's just a special one. It's a horizontal. So that is what a piecewise function is. And you might be sitting there going, holy cow, where is this ever used? And it's actually very quite common where you could have, say, a population of animals growing at, say, a somewhat linear rate. And then you introduce a predator or something, or the food supply starts to, drop off, and the population levels off for a while and then starts to decline more in this case, at a quadratic rate. So it's things changing over time will create possible situations for using different functions. So it actually, a piecewise is quite common. All right, so now when we look at this crazy graph, what's the domain? Well, everybody can go in. But look at the range. We never go above the 2. So it's -∞ 2, 2. The x-intercept is -3. And the y-intercept, I don't know how to do this right now. Oh, by the way, you will in Unit 8, but somewhere between 3 and 4. And that's the best we can say right now. So we have two x-intercepts. It's hitting here at the x-axis and somewhere in between 3 and 4. And then finally, the y-intercept is 2. So we've introduced you to sort of 8 different families of functions. And for 7 of them, I was able to give you what is called the parent function. It's the most basic function. So you kind of have an idea when you see a certain function rule, what the graph should look like. And then what we're going to start to realize is we can look at a function rule, know that it's going to be a line, or know that it's going to be a v, like an absolute value, but then it's going to move, it's going to shift, it's going to change. And we're able to look at the function rule and make sort of already guesses as to what's going to happen with the graph. But if I'm graphing an absolute value function and I'm getting a line, I know something's up and I got to figure out what that is. So that's kind of where we are today. You should have a perfect reference guide of the family parent functions. Again, number 8 is just an example. There isn't a parent piecewise, but we're going to go from there and start complicating them a little bit and graphing more complicated family functions. So guys, I hope you have a great day.